I'm development manager for the Compute Platforms Group at CSC IT Center for Science in Finland. So we're the Finnish national HPC center. We have about 60,000 cores, a big Cray with 40,000 cores, and a cluster with 20,000 cores, and a bunch of Xeon Phi's GPUs, big memory nodes, everything, and OpenStack-based cloud as well. So we run the whole gamut. And one thing that we've been really looking at also are containers, and we're just starting to work on them. And a lot of what I'm going to be talking is, let's say, what we've been thinking of where we can use them in the future, and what kind of research we are proposing for them. And basically, I think this is very good follow-up for the excellent talk by Jordi on, just focusing on containers and HPC. What's the big deal? Why are they important? So let's see. Let's turn this. Okay, so basically, making it easy to do custom HPC environments, but I think the first title was a bit better. So basically, what are containers? Well, we went through that already, and I'm pretty sure quite many of you are familiar with the concept. So can I see a raise of hands? How many are familiar with containers by now? Okay, so a majority. So just very shortly, so containers, basically isolated namespace sandbox where you can run your workloads, and it provides very lightweight layer of virtualization. So you basically share the kernel with the rest of the system. You get a really fast initialization, so sub 1 second typically, very low memory overhead, and a very negligible performance overhead. So basically, for a typical user, there's pretty much none. If you have some other experiences, I'd be happy to hear them, but we haven't seen any major degradation. And it's not a hugely new concept. So Solaris was doing it, IBM AIX was doing it, Linux has had these containers. Companies like Google have been relying on containers for ages. But in the recent couple of years, it's really been made popular by these new products, most notably maybe Docker, but also I should mention the LXD we're going to be hearing about, and I'm going to be very interested about hearing that talk, because I'm not that familiar with LXD actually, and what it can do these days. So really looking forward to that talk, as well as Rocket and a bunch of others. So there's things coming up pretty much every day, it seems. So basically, Docker is the major player these days. So what is it? So basically, it's a management framework for these Linux containers, and the key thing that's made it quite popular, I think, it's quite easy to use. It's quite accessible. So they, the first thing they started working on is making it really easy for users to get up and running. So previously, these containers had been quite complex. Just basically doing LXC was quite difficult. So it's quite stackable. So you can have a big base container and quickly just put a diff of another container on top of it, and you can install applications in a very low overhead way. So it doesn't take much storage overhead. It doesn't take much memory overhead if you run two different versions of a container, of a base container. And it also allows for rapid prototyping and development. So building up different versions of these applications on top of these base containers and throwing them away and modifying them and seeing what works and what doesn't. So it's quite good for this kind of development. And it also has this simple sharing of containers through the Docker Hub or private repositories for institutions. But one thing, it also has this kind of microservice type mentality that one process per container philosophy, or one active process. So you have your web server in one container, you have your database in another, and so on and so forth. And it's kind of grown and become this complete ecosystem. So they want to own everything with Docker, so all the orchestration and configuration and whatever. So it's they're adding a bunch of stuff there constantly. So and this is the basic simple picture. Many of you probably have seen that instead of having the full guest OS with a virtual machine and binaries and libraries, you can have a very lower. This basically kind of is the same as the overhead you have when you're running these different applications. So you can have much denser packing, and that's what it's really designed for, dense packing of virtual machines in nodes, and that's not that much interesting in from an HPC context where we really want typically a lot of performance, but I'll get to why this stuff is relevant anyway. And one thing is that the adoption has been incredibly rapid, so huge amount of contributors, huge amount of projects, a lot of job openings as well. The amount of applications have increased dramatically. So, and this is just like June 2015, so it's probably a lot more, widely used these days. And there's like 500 million downloads of these containers. And the interest in HPC is growing. So Jordi mentioned shifters, so that's pretty well known now, that, and that Cray is developing this. They've already supplied a patch that's kind of official for their systems. And then one interesting tidbit from a big US procurement is that they actually have set up this kind of desirable feature to have containers in their system, and I think this is something also that will drive a lot of the vendors in this space to really try to support containers, because if a big US lab with a lot of money wants container support, that probably will happen in some form. So and that's quite interesting. And one thing that kind of I look forward to in containers is not just the performance, but if you look at system-wide performance. So here's kind of like, if you have a full system, which is quite nice, we have very high utilization, and this is our Cray. So this line here is the capacity, and this is the amount of core used, and it looks kind of like this these days, so it's quite highly used. We'd like to have some more money, by the way, for a new system. But this is how things stand right now. But we can deal with it. So here we can see, the green one is the running number of jobs, and this purplish thing is the queued number of jobs. So it quite nicely, there's some peaks, but then over the weekend it gets smaller, and it can backfill and do all this clever stuff. But when you get to this situation in OpenStack, you get this. So basically, screw you, I'm not gonna schedule your job because my cluster is full and I can't queue it really. So this kind of like, and if you have this kind of load in the cloud, you'd probably be somewhere quite low, because you always have to over provision a bit to ensure that you have full nodes available for your instances. So the nice thing with containers is that they're quite simple to run, just like very quickly spin them up inside your batch job queuing system. So you can basically get all the benefits of backfilling and queuing and QoS and what for example Slurm provides these days. So this is, I think, a major thing that is speaks for using containers. So current choices for HPC workloads, basically, if you start looking at more deeply the use case. So here we have the bare metal HPC and cloud HPC, and these are not the market share or anything. It's just I made this bigger because there's a bunch of different small use cases here. So basically, for bare metal HPC, we have our site-supplied applications that our application specialists build, and then the user-supplied applications which they kind of compile on our systems or bring themselves, and the commercial applications. So, well, we use Slurm, so this is kind of like, yeah, Slurm, everyone should use it. If some application has very deep ties into some non-Slurm batch system, whether it's LSF or SG or something, if it has its workflow very deeply tied into some batch job queue system, you might be happier just to run the different batch job system in the cloud. Or if you want some special Linux distribution that you don't support, we run CentOS, but on occasion there's someone who kind of would like to use something that's very tightly designed for Ubuntu, for example. Or of course there's a bunch of people who just need and want root for some reason or another. Sometimes it's a very good reason, sometimes it's not. Typically it's not, but it might be just easier to give them root and take this cloud instance and go play. You also may want to preserve your software stack, so if you want to reproduce stuff. And you might have a lot of applications are these days supplied in virtual machine images, so if you have the image, it's simple to go to the cloud. Or one thing is Windows, so some people like to use some Windows stuff. I don't, I'm not gonna say anything about them, but it's fine, and we try to support it, so Windows is there. in the cloud. And some people want to do workflows with web servers, and and also some sites that we used to have as hosted sites, so they buy their own bare metal iron and they upgrade it, or we buy it for them. So instead of having this like bare metal iron, they're increasingly moving to cloud because it's quite a lot easier for them to then scale up and scale down, and they are fine with the slight trade-off between performance. And we're quite happy because we don't have a bunch of islands of different hardware. So so now we're getting to let's see. Okay, there we go. And secure access. So we have some users who really want an isolated space, and they want optical private network to their cluster instances if they use like medical data, like genomic data or something like that needs raised level security. And if you just have a complex stack which is very difficult to build, it might be better off to do it in a cloud. So with containers, it kind of changes. I foresee it changes like this. So we still have the demand for cloud HPC, so the hosting of the web servers running Windows, because you have because you have the Linux kernel in the container, you can't really run Windows. Either some applications will still be in virtual machine images, and the secure access, you pretty much still want to keep it in this cloud, and we've kind of built quite a lot of functionality to ensure these private network connections to our cloud for these customers. And but yeah, for containers, it takes a bunch of, it's very feasible for a bunch of these other ones. So non-Slurm batch queue system, Linux distro needed, I1 root, preserving the software stack, having the complex software stack. So there's a lot of these use cases that might be more feasible with containers. And also if you have containerized apps, okay, my animation is a bit broken, so those should have been there. Anyway, so example case, my application needs distro X, so you have one alternative, you adapt your application. It takes a lot of time and work to work on your bare metal HPC system. It might not even be possible with some ISV codes. Or you can run it in the cloud. Yeah, your customer gets to play cluster admin, so if they have their own cluster set up, and that might not be very efficient. And as I mentioned, the scheduling is quite limited. And also, if you just want to run a short job, spin it up, spin it down, it also has this initialization overhead. With a VM, it's like typically tens of seconds. So, and there's the performance penalties. So with containers, you don't need to touch the application, you don't need to, take time and work to adapt it to your HPC environment. And it's nearly as easy to run as a normal job in the batch job queuing system. So I'm not guaranteeing this yet because we haven't really done very robust testing on parallel job and stuff like this. And of course, there's very little overhead, as was mentioned already. So and you can use the normal batch job scheduler. So some challenges, just in particular with Docker. So the security model is quite problematic. So Docker is initially designed for server environments. So basically, the only one who can spawn up a server there is a server admin, and we trust these people. We have 2,000 users. We trust them to some extent, but it's we don't maybe it might not be a good idea to have an open system with that amount of users from multiple sites having the possibility to do this, because it's quite easy to root the server with this Docker if you're malicious. I don't know, you can counter me, but that's how because you can touch stuff, bare metal file systems, device drivers, access to raw devices as root privileges. You might be able to mess around with firmware. You can go to a shared file system, look around there all over the place. So there's a bunch of things that would happen if you want to do bad stuff with just the regular Docker. And it also requires these like special kernel features and a relatively new version of Linux OS. So these days with CentOS 7 coming into a very regular use, it's not much of a concern yet, but some sites are a bit conservative about distros. Like us, we run mostly CentOS 6 still, because we bought the machines then and the driver support is very good and stable. So that's a bit of hurdle still. And of course, like with Cray, you have this special compute node Linux, which is quite, it doesn't have a lot of bells and whistles. And also the daemon must run on every compute node, so that adds a bit of overhead. You have like a daemon running on all of your compute node, especially like on a Cray where they want to just like cut all the extra fat off the compute nodes. So shifter, that was mentioned, so it's really this kind of Docker containers for HPC. So basically what it does is it cracks open the container, takes the container stuff away, kind of flattens it into just a file system, and does some like tricks to make it a bit more secure, and you don't need like pretty much any container support in the operating system, and it integrates with batch job queuing systems like Slurm quite nicely, and you don't need to run even a daemon. So it kind of like you can take your Docker supplied image and adapt it to like a shifter image, and then you can run it pretty much everywhere. And it's developed by NERSC for Cori, and then Cray thought it would be a really good idea to productize it and release 1.0 support in March. And quite funnily, this 1.0 support is for PBS-based batch job queuing systems, while NERSC's original work is mostly on Slurm, so I have no idea what's going on there. So that's been a bit of a hurdle for implementing this thing. And well, there's like, they have a NERSC has a repository here in Bitbucket. I'll share these slides so you can click on the link. And there's not that much documentation there, but there's a bunch of papers also on the NERSC site about shifter.
They actually just moved to GitHub within the past few weeks.
Oh, they did?
Yep, and there's more documentation on GitHub now than there was on Bitbucket.
Yes, also on how to deploy on a regular cluster.
There are people working on deployments on regular clusters, myself included.
Oh, that's cool. We should talk.
Hopefully there will be better documentation within the next few weeks/months.
Okay,
but there are a lot of us working on it.
That's really good news. And of course, I mean, if because I haven't had a lot of first-hand work, I haven't been doing a lot of first-hand work on shifter, I'd be happy to hear what you have to say, or what you think about it. So basically, they have this. There's this concept of an image gateway that basically takes the Docker containers and adapts it to these shifter compatible images, and you can then run it. And here's some results I stole or borrowed from NERSC that basically shows one nice feature that actually, when you take some big complex Python code where you have a lot of different Python files, and it does a lot of metadata ops, when you run it on the regular parallel file systems and these kind of project file systems, the metadata ops are a lot slower, but if you have it containerized in this kind of shifter image, then the metadata ops go on the local node, and basically it's kind of very close to what TempFS can provide. So you get actually like a performance improvement in this case with using containers, so that's quite nice. Have you seen this kind of performance?
My group doesn't have a working shifter implementation yet.
Okay.
I've talked to Doug and Shane at length, though, about the performance numbers. But yeah, that's why they chose to do it that way.
It's quite nice. We have a couple of science applications which use Fortran at their core, but they're basically Python frameworks, so all the non-performance critical stuff is with Python, and there's thousands of files. So it would be kind of a really nice use case. And we have our parallel file system full of we have 850 million files there, so having those packaged in images, at least some of them, that would be really nice. It causes some issues in recovery if you have that many files. If something happens there. Anyway, so one new kid on the block, or it's been developed, I guess, for a bit, is Singularity. So I started playing with it quite recently, and it looks really interesting. So how many of you have been, are aware of this or have been playing around? Okay, a couple of people. So so basically, the approach there is it containerizes only the workload and its dependencies, so the binary, the libraries, the input-output files, so on and so forth. And the configuration is stored in an spec file, which is kind of, if you know RPMs, they have a spec file, so it's kind of like a similar thing. And here's a very simple example, and it's basically, you can have the files that you include, and then it kind of figures out the dependencies, and then you have a run script of that you can do some workflows, you can put multiple things in there, and the S spec is I can if I have time I can do a very quick demo if my network is okay. So the SAP file then the spec file can be then baked into this SAP file, and that is like a file that contains the workload and all the dependencies. And okay, a miner that can run anywhere where Singularity is installed. Sorry, that's kind of like promising a bit too much. But it's very simple to install. So if you go to the Singularity website, it actually it's very straightforward. It's quite small and simple, and I really kind of that's one thing why I like it as well, and one thing why it was very easy to just in a couple of hours to test out the basic functionality and get it running. And it supports MPI out of the box, and it's developed by Lawrence Berkeley Lab, and as I mentioned, a couple of days they came out with this 1.0 release, and they have a nice website, Singularity.gov, and they have a really good FAQ where they answer a bunch of these kind of questions, how this differs from Docker and how this differs from Shifter and so on and so forth. And quick summary. So what I see, Docker is really good for in the context of HPC is really like looking at rapid deployment, prototyping and deployment of stuff, playing around with different versions of libraries and things like this, running stuff on your laptop. Shifter, then it's nice because then you can take the stuff you've been working on here, and then it works directly with Docker containers. You don't even need the container support. And then with Singularity, you can go a bit deeper, package the single application or a workflow in this, one single blob. And I tried Ciano, which is quite a complex machine learning framework, to just package it into one of these, and it was about 6 megabytes. So it's quite, compact, and but you also need to ensure that all your dependencies are there. So sometimes this Singularity command that does the spec file, I can show you that it can generate it. It might not, get everything with a single run, with a single input. So it kind of, it might miss some. I haven't really seen that yet, but I could expect that it might miss some dependencies. So it might need some manual tweaking of the spec files. Whereas with Shifter, you can quite simply take whatever is in Docker Hub and do it. But as Jordi mentioned, it's important to know that containers are also not a magic bullet. So it's kind of like the same thing as pulling scientific software from an RPM repository. So if you take it from Docker Hub, so it might not be optimized for your architecture, and you can still yourself build your app very badly. So if you're lazy, you just I'm going to do it manually, build it into a container, throw it there, let it rot, not document anything. So it's you still need to maintain your applications and libraries. You might get divergence, so you might have tens of these base images which can take gigabytes, and debugging this stuff might be a nightmare. If you have users who have containers and they've just put a bunch of stuff in there, and then it breaks, and they're like, can you help me? And going in there might be a bit difficult. And also, you'd want to also, if you do some automated builds, you want to test each new release, and you want to keep the containerized stack optimized, so for the newest vectorizations and everything. So automating a bunch of that stuff would be important. And also these multi-platform deployments and sharing. So if you want to share, if you built an application, you want to share it with other sites, depending on what they use, if it's bare metal or whatever, you might need scripts or, sharing specs. Docker has Docker files, you use Ansible or something, you have playbooks, so there's, it can get quite, divergent. So, should the application configuration and this level of configuration, when you build your system, be decoupled from the containers? And my answer is really yes. And one thing is, easy build, which will be discussed here. So I kind of believe that, because easy build is really designed for managing these software stacks. You can basically, I envision you can use single config for multiple targets. So you can target with the same application config, the bare metal, virtual machines, Singularity, Docker, whatever. So you can basically, use even these today, the easy build configs, you can just install it and then just use it with all of these. And I think the EasyBuild guys tweeted at me at they're actually looking at Singularity and putting some support so that or considering putting support that they can do these spec files for Singularity. And also one thing is that with EasyBuild, it will be discussed in more detail, but you can keep this in mind when EasyBuild is being introduced if you don't know it. So you can also think of it as a way to create these well-built base containers. So having all the libraries, compilers, all the base stuff, very well optimized, and then you can give these containers to the users, have them customize it to their needs, and you still kind of like can maintain the base or standardize between sites on these containers. So you have like something to build on. So I think this would be a really good model. But also it's a bit like which way to do it. So using EasyBuild in a container and building the stuff there, or then building containers with EasyBuild, which then might have some extra support from EasyBuild, but it might be a bit more elegant way. So it's kind of you can do it kind of both ways, I guess. Some future challenges, as I mentioned, encouraging users to do the right thing. So for a lot of use cases, bare metal is still the best way, and putting in like the work to utilize the really nice base environment which many of your HPC admins have set up on your site, and using containers only when needed by these use cases. So if you try to use it for everything, you soon will have a divergence where you don't your well-built container stack will get ignored, and people have like semi-well-built stuff like all over the place, so a bit of house cards. So also promoting these well-maintained containers, for example, through EasyBuild. Also, encouraging users to avoid insecure containers, pulling just random stuff. Thinking a bit about what they do. Same thing actually goes with regular applications, so it's nothing new in that sense. But this might make it this kind of
pulling these containers might make getting these third-party applications much simpler. So there should be some kind of people might start pulling like all kinds of random stuff, and deciding really which container systems to support. So I don't know, it's constantly evolving. So should we support Singularity or Shifter or both? LXD, I'm really interested in hearing how that plays into this. So it's constantly evolving. So now we try to look a bit of everything, and really also try to get everyone involved in looking at this, and kind of together we can maybe figure out what's the best way to use these things. So it might be that Shifter is good for something, whereas Singularity is good for something else, and they can play together somehow. And also this developing and sharing good base containers. And one thing that's kind of low level is this kind of driver issues. So you still have the Linux kernel there. You have your certain version of a driver, for example, for CUDA, or some flavor of InfiniBand drivers, and then on the container you have some version of OFED and some version of maybe like the higher level CUDA stack, and there might be some incompatibilities there. So how do we kind of ensure that those situations kind of get handled, or we avoid them? And if someone already has some good practices there, I'd be interested in hearing it. And also this kind of looking at containers for the system management and services side. So really having like microservice-based service nodes. So we have a couple of containers for Slurm, and those can run pretty much everywhere for the Slurm database. Another one, and look at how that could make the service nodes more resilient and more scalable. And also like looking a bit like at containerized parallel file systems. So instead of having a HPC workload there, maybe we could run Lustre or BGFS or whatever, like or Ceph in like quite ad hoc set up something in a bunch of containers, even by the users. So that might be kind of fun. So that's it. So I might have time for a demo.
Yeah, well, you've got 10 minutes, yeah.
Okay, but are there any quick questions? Okay.
Start off with the demo.
Okay, I'll just download, and it has quite simple options. So what I want to do is spec gen. So generate a spec file based on a given command. So spec gen a.out.
Okay, well that input error, that's from the output from the application, so it does a test run. Okay, now even in that case it did this wrote A out spec, and here it did it again. So so if I go to look at this A out.s spec, it basically shows what I did and what's the run script, and this is basically if I give the singularity command a parameter where it puts it, and then it includes the files, including the output file, which is timedgem, which is the timing file. Well, I can just use this now, and I'll just out of curiosity, I haven't looked at okay, there's about well, this is the latest one, 17 gigaflops or something. It's quite a small dgem, so it's not super good. But I just did it short because of time. So then I can take the singularity, and then I will build A out S spec. And now it basically goes through and bakes the SAP container, and now I have A out.saap, and now I can basically do this, and now it basically ran the same command in a container, and basically now I can take this container, take it to a system that doesn't have this version of OpenBLAS, or this OpenBLAS I linked it to, which was included there, and it should work. So, and if I look at the timedgem, okay, it's actually a bit faster. So it's 22 gigaflops, but these are so small things, so it might have something cache or something. So basically, the performance overhead is negligible. It can start quite quickly. The only thing is that for this very small application, the binary grew a bit, so it's about what's it? 12 megabytes, so it's quite a big chunk, but if you have a more complex application, it might make more sense. So one thing I also did is this is a very simple. I just import piano in this Python script, so I can do a singularity spec gen and Python. I haven't actually really tested how well it works, but okay, it wrote this Python S spec, and basically it's 58 kilobytes. So if we start looking at it, it basically imports a bunch of Python packages from this piano, which is and SciPy and all this stuff. And I can actually then, that was fast, but then if I start building it, then it takes a while. But I cheated a bit, so this takes about 5 minutes. But I'll just kill it. So in the end, this okay. I must have let's see. Okay, this is the final Python S app. So it's about 86 megabytes. So it's not super small, but for this kind of complex application, it's still reasonable. And then basically, here you have a nice package version of Piano and all its dependencies. I haven't really checked if it's all there, but at least you probably should be able to run some basic stuff. So this is very much a work in progress, but this is just a demo on how easily you can bake these singularity files. Anyway, so any questions on this, or just one comment on this, that it actually needs one file to run a setuid root if you want to install Singularity, so you need to have root access, and thus far we've been really testing this on our cloud and on our VMs, so not in production yet. So.
Come on guys, now it's the time to ask questions. So I have one. What about user education? How do you deal with that in your specificity? How easy is for the end users to get this knowledge to be able to deal with that thing?
Well, we do a lot of courses, we do a lot of road shows, and but we have a user base that kind of gets renewed, and it's kind of very varying degrees of expertise, so it's quite a challenge. So we're kind of like haven't really even thought about best practice and how to sell these containers and how to tell users how to use them properly and where to use them properly. So yeah, that's a good point. We need to figure out, and if you have any ideas, I'd be happy.
Okay, thank you.
Thank you.
Thank you for this nice presentation.